Here's the final problem in the fundamental section for power and efficiency. This is a nice problem because it incorporates several different sections. In order to solve this, you need to understand things from chapter 12 and from chapter 13. Let's see how it goes. At the instant shown, point P on the cable has a velocity of 12 meters per second downwards, which is increasing at a rate of 6 meters per second squared. Determine the power input to motor M at this instant if it operates with an efficiency of 0.8 or 80%. The mass of the block A is 50 kilograms. Okay, well, again, let's start off by listing what is given in this problem. So the speed of the point P is drawn there. The acceleration, 6 meters per second squared, is also drawn. But let's make it clear that the mass of the block A is 50 kilograms, and the efficiency of the motor is 0.8. That means that within this motor, when we plug it into the wall, every 1 kilowatt we put in there, we only get out 0.8 kilowatts. The rest of that remaining 0.2 is just lost to heat or noise and other irreversibilities that occur within that system. Okay, we can't get every single unit of power out that we get putting into our system. Okay, so how do we go about solving this problem? Well, we recognize that in order to solve for the power into our system, which is what they're asking for, well, how much power do we have to put into our motor? Well, that's going to relate to the efficiency. And the efficiency is equal to power out divided by power in. So we know what the efficiency is. That's 0.8. If I knew what power out was, then I could solve for power in, and I'd be done with this problem. Let's remember what power is equal to. Power is equal to F dotted with V, or it's equal to FV cosine theta. All right. So this motor here at M is attached to one cable. It's pulling in this cable, and we know how fast it's pulling in that cable and the acceleration of that cable. That's given to us in that little box there. So we know that the cable is being pulled in at 12 meters per second. That's the speed that we're talking about. That point P on the cable is currently moving down 12 meters per second. That's the speed of the rope. But we don't know what the force is on that rope. The force in that rope, which we usually call the tension, is unknown to us. So we need to solve for that force. But recognize that I know the direction of the force, even though I don't know its magnitude. At P, the force is being pulled downwards, which is in the exact same direction as both the acceleration and, more importantly, the velocity. So cosine of theta, in this case, theta is equal to 0 degrees, meaning cosine of theta is equal to 1. I will not have to concern myself with this last part because the force, the tension, is in the exact same direction as the speed. They're both downwards constantly. Okay? So all I need to do is solve for the magnitude of that force, which is the tension in the rope. How do I do that? That's a good question. Well, a great way to solve for forces is to draw free body diagrams from chapter 13. Here is my weight at A. Well, what are all the forces acting on A? There's the weight of the object itself, which is the mass times the acceleration due to gravity. And there's also 2 tension forces pulling up because it's attached to a rope here and a rope there. So ultimately, there are 2 tension forces pulling up. No free body diagram is complete without a set of coordinate axes, so I'm going to call x positive upward, positive to the right, y is positive upwards. And just to make it complete, here's my kinetic diagram. The same block, I assume that this thing is going to start accelerating like that. Okay? Well, if that's the case, then all I need to do is sum my forces in the y direction, set it equal to mass times acceleration in the y direction. 2t minus w is equal to mass times the acceleration of the block. Uh-oh, I don't know what the tension force is. That's what I'm trying to solve for. But I also don't know what the acceleration of the block is. So I need to stop and think about it for a little bit. Is there a way where I can solve for either the tension or the acceleration using something else that I've learned in this class? And hopefully you're already seeing it. The answer is yes, we can do that. Whenever we see one of these pulley problems, we should immediately start thinking about how we solve for dependent motion. I'm going to define two position vectors. I'm going to call this position vector SA. And I'm going to call this position vector to location P SP. I'm going to write the length of my cable. The total length of my cable is equal to SA plus SP. The first, oh, that's not right. It's equal to 2SA. So I have 1, 2 SAs, and then I have a single SP. So the length of the rope is 2SA plus SP. Take the first derivative, 2VA plus VP. Second derivative, 2AA plus AP. Aha! So I find out that the acceleration of block A is equal to negative 1/2 the acceleration of block P. The reason why I have that negative sign there is because as point P goes downwards in its positive direction, block A goes upwards, which is in its negative direction according to my dependent motion analysis vector, SA. All right? But all I care about is the magnitude. I know that the acceleration of point P is 6 meters per second squared. That means the acceleration of point A is equal to negative 3 meters per second squared. That negative right here indicates that block A is moving upwards, which is exactly how I drew my acceleration in my kinetic diagram up here. So when I plug in my acceleration now into this equation, 2t minus w is equal to mass times acceleration, I'm not going to put in negative 3. I'm just going to put in a positive 3 like that. Okay? Why is that positive? Because I know that the block is moving upwards based off my dependent motion analysis. And in my kinetic diagram, that acceleration was drawn upwards. So that's a positive 3. So the only unknown here is the tension. 2t minus the weight, which is 50 kilograms times 9.81 meters per second squared. It's equal to 50 kilograms times 3 meters per second squared. Aha, everything is in newtons. That's units of newtons. That's units of newtons. So my tension will be in units of newtons. When I plug this into my calculator, I find out that the tension within the cable is 320.25 newtons. This is the force that I need for my equation up here. The power out from my engine, or from this motor here, is the tension force, 320.25 newtons, times the speed of the rope as it's being pulled in. The speed is given to us, 12 meters per second. This is equal to 3,843 watts, or 3.84 kilowatts. If I want it like that, you could write it either way that you want. Now, if my motor were 100% efficient, I would only need to put in 3.84 kilowatts to get out 3.84 kilowatts. Everything that went in would come out. But unfortunately, my motor is not 100% efficient. As I said before, it's only 80% efficient. So I actually need to put in more work or more energy into my system more power into my system to get this desired amount of work out, or power out, 3.84 kilowatts. So how do I do that? I have to go back to my efficiency equation. I've just solved for power out. I know what the efficiency is. I just simply need to solve for power in. So rearranging that equation, power in is equal to power out divided by the efficiency. Power out was 3.84 kilowatts. The efficiency of my system is 80%, or 0.8. So power in is 4.8 kilowatts. I need to put in 4.8 kilowatts. Maybe this is in the form of electrical energy. We plug this thing into the wall. Or maybe it's gas powered, I don't know. Something is being put in. The power is being put into the system in some manner. Maybe it's plugged into a wall, so it's electrical energy. Maybe it's gas powered. Maybe it's coal fired. I don't know. Maybe it's a nuclear powered motor. Probably not, but maybe. But I need to put in 4.8 kilowatts of power if I want this system to operate as I've shown it here. Okay? Power out is 3.84, but the power in is 4.8 kilowatts. I need to put in more power than comes out because no system is perfectly efficient.